Hello guys, my name is Amay and I am a student of IIT Bombay Mechanical Engineering Department. I am currently in my fifth semester. Today we'll be continuing our topic integral calculus, and the subject for today is Riemann integration. So why is this topic important? Because it is the first rigorous definition given by anyone to define the integral of a function. In this, we have used very simple approximations along with the Riemann sum to estimate area under the curve. Such techniques are also important for study in numerical analysis, which is widely used in several branches of engineering. So, similar to Darboux integrability, which we had studied in the previous video, here we will again define the partition P of x0, x1 up till xn as follows. We have divided this partition into n parts. We define norm of P as the maximum difference between any two xi's. So here max xi plus 1 minus xi will be defined as norm P. The only difference between this and Darboux integrability is that we add something called tags over here. So basically a tag is some point between the subinterval. If I take the tag ti, then it will belong to the interval xi and xi plus 1. Similarly, every subinterval which we have defined here will contain a tag. So we define the Riemann sum as S of f comma p comma t, and here again we do the summation of the rectangles in each interval. The difference here is the width of the rectangle, and instead of taking one of the endpoints like we did in the Darboux sum, we take the value of the function at ti, that is this tag. So depending on different values of ti, we can get different types of sums. If ti is xi minus 1, that is the left endpoint, then this is defined as the Riemann sum. The graph for left Riemann sum is this one. If ti is taken to be xi, that is the right endpoint, then this is defined as the right Riemann sum, which is given by this graph. If we define ti as xi plus xi minus 1 by 2, which is the midpoint of the interval, then we get the middle Riemann sum. Here you can see that the function is taking the value at the midpoint of the interval. If ti is the supremum of f of xi minus 1 to xi, then this is known as the upper Riemann sum. In the previous video, we had seen that this is also equal to the upper Darboux sum. Similarly, if ti is the infimum, then this is known as lower Riemann sum or lower Darboux sum. So the criteria for a function to be Riemann integrable is as follows. All Riemann sums should converge as the interval becomes finer. That is, the difference between xi plus 1 and xi should become less. So this is the formal definition for integrability of a function. F is said to be Riemann integrable if there exists a delta greater than 0 for all epsilon greater than 0, such that this modulus, that is the Riemann sum minus s, is less than epsilon for every tag partition p comma t, such that norm p is less than delta. This s is the value at which all Riemann sums converge, and this is known as the Riemann integral. So which functions are Riemann integrable? So these three functions can be considered Riemann integrable. The function should be continuous in the interval a comma b in which it is being integrated. It may also be monotonic, that is either increasing or decreasing, or it can be bounded in a comma b and continuous except at finitely many points. This condition, the third condition, can also be written in a different way, which you may have read in certain books, that f is integrable on a given domain if points of discontinuity is a set of content 0. Here we need to look at two important functions. First we'll look at the Dirichlet function. That is, fx takes the value 1 if x belongs to rational and 0 if x does not belong to rational. we should remember this fact that this function is not Riemann integrable. Here is the graph for the function. The proof is quite lengthy, and honestly it is not necessary to be studied from an exam point of view, but this fact should be remembered because it may be useful while solving questions. Similarly, we define a function called Thome function where fx is 1 by q if x is p by q, that is x belongs to rational, and 0 if x belongs to irrational. However, unlike the Dirichlet function, this function is Riemann integrable, and the integral over any interval evaluates to be 0. So let us look at an example. We have the same function which we had in the previous lecture, fx equal to x, and we have to prove the Riemann integrability of this function over the interval a comma b. So we define the interval a to b, and we take different values of xi, and we also do the additional step over here, that is define the tags. So here I'll take the tag to be midpoint of the interval plus some difference di, such that this difference di should be less than the distance of the midpoint from either of the endpoints. So here we know that di is less than xi minus this term, which will give xi minus 1 by 2. So also we know that norm of p is defined as the maximum of this difference. So this difference will be less than or equal to norm of p divided by 2. Now we define the Riemann sum as this, and substituting the value of f of ti, we get this, and on summing this, we will get b square minus a square by 2. This is basically a telescoping series. So all middle terms will get cut and you will only get the first term and the last term. And this summation over here. So this entire thing should be defined as the this b square minus a square by 2 is defined as the Riemann integral, and all sums Riemann sums s f of p comma t should converge to this value. So we define this mod Riemann sum minus Riemann integral, and using the property of modulus, we can say that this function is less than mod of di into this interval. We know from this property that mod of di is less than norm of p by 2, so we can take this out and we get this sum. So for n tending to infinity, we know that this term will tend to 0, so we can say that this difference tends to 0 as n tends to infinity. So we can see that this Riemann sum is converging to this Riemann integral, and so we can say that fx equal to x is Riemann integrable on this interval, and the integral for this function is b square minus a square by 2. In higher dimensions, we need to define the domain as union of union of ai and aj over the x and y intervals. So, and even in this, the tag will also change because I and j will both take different values. We need to divide the x part of the interval into m sub intervals, and the y part of the interval into n sub intervals. Basically the same thing that we have done for 1D but in 2 dimensions. So Riemann sum here can be defined as I equal to 0 to m minus 1, j equal to 0 to n minus 1, value of the function into aij. And similarly in 3D, we just add one more dimension here and make it aijk. So here is a question which you can solve. We have to check the integrability of fxy equal to x square plus y square in this rectangle. So here we can take tij as this. This is the tag we can take, And as I said that I can be divided into m subintervals and j can be divided into n subintervals. Similarly, you just have to substitute these values in this to find f of tij, and then multiply it by aij, that is xi plus 1 minus xi into yi plus 1 minus yi, and take the summation, and you will get the Riemann sum in terms of n. And when you take the limit n tending to infinity, you will get the Riemann integral. So thank you for watching. Scan this QR code to know more about us, and see you all in the next video.